So my name is Jason Steffen. I'm a physics professor at the University of Nevada, Las Vegas, and this is coming from my live stream. We're going to do one take. Of course, it might end up being multiple takes, but we're going to start with one take, and then we're just going to blaze through it for my favorite number that is larger than 1 million, at least today's number that is larger than 1 million. And that one happens to be, it demonstrates how much greater physics is than chemistry. And that is 602. 214076, and then a whole bunch of zeros. 4, 5, 6, 7. So what do we got? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. This number right here. This is Avogadro's number. Avogadro's number is the connection between physics and chemistry. It takes you from the scale of physics up to the scale of chemistry and shows you that that physics is this many times better than chemistry. Of course, people might have different things to say about that, but they can be wrong. The reason that this number is particularly interesting to me is that the unit system for the SI, like the unit system that we use across the world, has actually changed. It made a significant change in 2019, and it was a change that had been in the makings for many decades. And it comes down to the fact that before this time, many of our units were based upon physical objects. If we look at the unit system before it existed in 2019, it was based upon a few measurements and also a few other things. So the unit systems are given here in this diagram. So there's the second, there's the meter, there's the amp, the Kelvin, kilogram, the mole, and the candela, which nobody ever talks about. This is kind of the black sheep in the family that is left to the side. So the candela is like luminous intensity. How bright does something appear? The mole, of course, is the transition between chemistry and physics. How do you go from things that physicists study to the things that chemists would study, is the mole. So that's kind of the scale between these two disciplines. Of these things, many of them were based upon either physical constants or physical properties. The time itself, seconds, is defined in terms of the frequency of a cesium atom in an atomic clock. So you count up some number of cycles in this cesium transition in an atomic clock, and that defines the second. You combine the second with the speed of light in order to get the meter. You combine those things together with the permeability of free space in order to get the amp, like the electric current. But this required, like the measurement of the electric current, required knowing the force between two wires separated by 1 meter with infinitesimal cross-section. So there's a lot of impossible things that go into defining the amp. Having them exactly 1 meter apart from each other, you run a current through both of them. The wires have to be negligible, which is impossible to do because every wire is going to have some physical size. And so some of these units are based upon scenarios, like idealized scenarios that you can't actually realize. The kilogram, in particular, the kilogram was based upon the mass of the kilogram, the big K. I can show you what this looks like. The international prototype of the kilogram was a piece of iridium alloy housed in Paris, France. So it's a cylinder of iridium alloy in this vacuum chamber. That is the kilogram, or at least it was the kilogram up to 2019. Different nations had copies of this kilogram, but the kilogram, and it was actually designed to have a minimum surface area so that, you know, it doesn't, because any impurities are going to be absorbed through the surface, and so you want to cut down on the amount of surface area so that you get fewer impurities that come into the system. That could be coming from cosmic rays, like stuff being embedded in it. It could be absorbing stuff from the environment, whatever the case may be. But the kilograms, actually, the masses of them diverged over time. And so every day, the actual value of the kilogram was changing imperceptibly for the most part, but it was still changing because this was the kilogram. And it's not a very happy circumstance to have the entire system of weights and measures across the globe determined by some artifact that's located in Paris. Not that Paris is a bad place to visit, but that's what we were stuck with. Before this, the meter was actually defined in terms of an artifact, like the meter was a length of the same substance that was 1 meter long. Before that, the meter was designed as 1/10 millionth of the distance between the North Pole and the equator along the prime meridian. And so there were a variety of definitions, and over time, as our ability to measure things has improved, then the need to have better standards has improved along with it. And this was one of the major breakthroughs, is how do you deal with the kilogram? Because this was kind of the last holdout in terms of how our units are based relative to the universe, and what we can do. How can we tell what a kilogram is compared to something else? So the kilogram was based upon the mass of an actual artifact. That was the definition of a kilogram. The mole is determined by the mass of carbon. You say, I have 12 grams of carbon, and based upon the kilogram, so the kilogram tells you what a gram is. So the mass of the carbon atom then tells you what a mole is, because you say a mole is 1 gram is 12 grams of carbon-12. So if the mass of the kilogram changes, then Avogadro's number, the size of the mole, actually changes along with it. The number of carbon atoms that go into making a mole changes as the mass of the kilogram changes because of its interaction with its environment. In 2019, they redesigned the entire metric system. This is what the new metric system looks like. Now, all of the units of the metric system are based upon fundamental constants or declared constants. So you still have the speed of light, you still have the cesium oscillations of the cesium atomic clock. Now, however, the amp is measured rather in terms of the force between two wires separated by 1 meter. The amp is determined by the charge on the electron. So the electric charge tells you what the amp is, not the force between two hypothetical wires in a scenario. Boltzmann's constant now tells you what the Kelvin is. Before this, the Kelvin was measured as the triple point of water. You go to the triple point of water, where water exists as a vapor and a solid and a liquid at the same time. It can only happen in one place. It can only happen at one temperature and at one pressure. You go to that location, and then you divide by some number, and that gives you the Kelvin. That's the definition of the Kelvin. That has now been changed, and the Kelvin is now determined by Boltzmann's constant. Boltzmann's constant is now fixed. This is the definition of Boltzmann's constant, and that determines what the Kelvin is. Candelo has basically been the same. Now, Avogadro's number, which is this number that I wrote down, Avogadro's number is now fixed. This is the number of carbon atoms in 1 mole, or the number of objects in 1 mole of that substance. Now, there is some discussion about whether the mole is really a fundamental unit, which it isn't. It's a number. It's like saying that a dozen is a fundamental unit. Nevertheless, this is counted in the SI unit system of units, and now it's a fixed quantity. It does not change because the definition of the kilogram doesn't change either. The kilogram is now determined by Planck's constant. That gives the definition of the kilogram. Now the unit system is based entirely upon these fundamental either constants of the universe or constants that we declare, rather than on the properties of artifacts that exist in certain places, or things that are difficult to measure, or hypothetical situations that we cannot reconstruct. And that is why Avogadro's number is my new favorite number, larger than 1 million.